We're going to look at how to differentiate when we don't have an explicit relationship between x and y. So we'll look at something called implicit differentiation. Implicit differentiation. And I want to begin by posing a type of question that might encourage us to use implicit differentiation. Why do we have a need for this thing? So a very good example might be something like this, and we'll come back to it later and how to do it. But let's say for example, we have a circle in the plane like this, okay? And we would want to know the slope of the tangent line right here on this curve. And so at this point on this curve. And so this curve, this circle, is certainly not a function. And we'll see that if we were to write the equation for this circle, we'd get what's called an implicit equation between x and y. And so we'll come back to that later on so that we can see how to differentiate this and find the derivative or the slope of this tangent line. But before we get into all that, we need to establish some basic ideas. For example, I keep mentioning the terms explicit and implicit. We need to kind of look at what those are. So we're typically used to explicit equations, let's call them. Explicit equations are where you have your dependent variable, like y, your dependent variable equals an expression in terms of your independent variable. So let's write this like this in terms of, let's say, x. So if you want to calculate a y value, you can plug in an x value, and this formula will spit out y values very easily. Okay. Again, y here is called the dependent variable because it depends on the value of x, and x is the independent variable because the choice of x dictates the behavior of y. Okay? So that's what explicit equations look like. We know how to differentiate functions, right? Typically functions are good examples of explicit equations. We know how to differentiate functions that are in this form. But implicit equations don't define x and y so cleanly, the relationship between x and y so cleanly. So on the left side, you can have an expression with x and y, multiple x's and y's. And then on the right side of the equation, you can have another expression with x's and y's. And so these can be a bit messy to really understand the relationship between x and y. And oftentimes what you might do is you might take and plug in an x value to calculate a y value, or vice versa. But you can't plug an x value in and the formula tells you directly what y is. You have to do some more work in these examples. Okay? And I'll go ahead and point out an example of an implicit equation is the equation of that circle we just looked at. Perhaps an example of one might be x squared plus y squared equals 25. And in fact, before the end of the video, we'll come back and we'll do some implicit differentiation on this equation. Okay? But that's a good example. If I want to know a y value, I'd plug in an x value, and then I would solve for y to figure out what y value goes with it. Or vice versa. Okay? Now this is a pretty simple implicit equation, and we're going to start simple, but in following videos I'll have more examples where the equations become a bit more messy and maybe not as easy to understand. Now, let's talk about differentiation of the two variables y and x. Can be a bit tricky, especially at first, because you'll tend to make particular assumptions. So let's recall some things that we already know. For example, if I differentiate with respect to x. Now, we've been using this notation before, and currently what we need to know is that x is the variable. So that's important. But even more so, this is the independent variable of what you're differentiating. Okay? So we already know, however, that if I differentiate a constant with respect to the variable x, we know that that derivative is 0. So that's no problem. We even know that if we differentiate x with respect to x, that derivative is just 1. But what do we get if we differentiate a function of that independent variable? So this function f depends on the value of x. And so what's key here is that this variable x, independent variable x, matches this. And so this is a bit abstract, but the derivative of f with respect to x, well, the best we can do is we can call it f prime of x, right? So we know that already as well. We're used to that. However, lots of times in implicit equations we'll have x and y. And what's important to know about y is that y is the same thing as a function of x. So when you look at y, you have to think of it as being a function. It is a variable, but it's also a function of this variable x, okay? So it's kind of this hidden capsule of things. So if we want to now differentiate, and this is the point of all of this explanation, if we want to differentiate y with respect to x, well, see, the variables don't match. But we know that y is a function of x. So when we differentiate y, it behaves just like this differentiation of the function f. In fact, the derivative of y with respect to x, well, it's just dy dx. It's dy dx. Or you could call it y prime. Now, what I'm trying to get you to see is if you differentiate x with respect to x, you get the constant 1, okay? But if you differentiate y with respect to x, you don't have the same behavior because y is a function of x and it exhibits this behavior. All right, so make sure you understand the difference between those two. And sometimes the variables aren't y and x. You know, oftentimes in calculus, the independent variable will be t for time. And so this could be a function of time. And then this would be the derivative of y with respect to t. And you could say dy dt. But it's also called y prime, understanding that you're working in the context of the independent variable t. So y prime would be the derivative with respect to that variable t. Okay? But for the most part, we're going to work with y's and x's. So now let's go back to our example here involving the circle and how these concepts can help us. Now, if you recall the question, let's say we want to determine the slope of the tangent line to the curve. So if you recall the equation of the circle that I mentioned earlier might be x squared plus y squared equals 25. Keep it very simple. Again, this is called an implicit equation, okay? So I want to know the slope of the tangent line to this curve, which is the circle I drew earlier. And let's name a point. Let's say we want to know the slope of the line at the point 3, 4. Okay? At the point 3, 4. And so again, if you drew a picture of what's happening here, I can't draw a very good circle, but use your imagination, please. This particular circle has a radius of 5. So it would go out here to 5. It would come up here to 5. It's centered at the origin. Come over here to -5 and down here to -5. And then it would look roughly, very roughly, like this, okay? And so we would want to know the slope of the tangent line to this circle at the point 3, 4, which maybe is right there, right? 3, 4. And then the tangent line we're looking at is this guy right here. And we want to know the slope of that tangent line. So how do we do it? Well, if we want to know the slope of the tangent line, we're asking for the derivative of the function. Now, when we look at this, there is no function, but we understand that y represents the dependent variable. So when I want slope now, instead of thinking the derivative of the function, think the derivative of y with respect to x. And that even kind of looks like slope, right? It's like the change in y divided by the change in x, the rise over the run. And it's an instantaneous change in y over change in x. It's at this particular moment in time. So we need to know what dy dx is. So let's take our equation, x squared plus y squared equals 25. And let's do this to it. Let's take this equation and write it as a differential equation, an equation that involves a derivative. And now we know how to work with equations. Anything I want to do to the equation, I'd have to do to the left side and the right side, right? And that's also true with derivatives. So what we're going to do here is we're going to take the derivative with respect to x on both sides. All right, so this is going to be tricky, okay? So let's write it out, though. We're going to do the derivative with respect to x of the entire left side, and then I'll do the derivative with respect to x of the entire right side. And so I'll fill the left side and the right side in red again. The left side I've got x squared plus y squared, and the right side I've got 25. So I'm taking the derivative of the entire left side of the equation and balancing it out by doing the derivative of the entire right side of the equation. Now, the derivative on the right side is very simple because 25 is a constant, so the derivative is 0. The left side is also not too bad. It's a good introductory equation to look at. The derivative of x squared, because the x's are the same, well, it's just your typical power rule. So the derivative of x squared is just 2x. Now, this is where it gets tricky. The derivative with respect to x of y squared. Let's take a minute and sort of explore that over here fully, okay? Think of that as being the derivative with respect to x of a function squared, right? Because y is like f of x. It is our dependent variable, so it contains within it information about x. And if you were going to differentiate this, well, you would start by implementing the power rule. So you'd bring your exponent down to the front. You'd have 2 times f of x to the first power, that's a 1, to the first power, that's your power rule. But then, because the input to the square is a function and not the variable x, you have to implement the chain rule. Please write that down if you need to write that down. The chain rule, I'd still have to multiply by the derivative of the inside, which is f prime of x. So the power rule, but then because what's in the square is a function itself, I have to multiply by the derivative of that by the chain rule. And so that's what's going to happen over here. So I'm going to do the power rule first. 2 times y to the first. So I'll just write 2y. But then, if you think about it as y being squared and y as a function, then you have to go back and do the chain rule and multiply by the derivative of y with respect to x. Well, it's a good habit, I believe, and after polling students for many years, they much prefer dy dx to y prime. Y prime can be mistaken as y to the first power. Dy dx, there's no mistaking that. That's the derivative of y with respect to x. You're welcome to play around with using y prime here. Just don't get confused. And later on, you may come back and decide you like dy dx anyway. But I'm telling you that students typically understand that dy dx is a better choice here. Okay? So now we have this differential equation. In other words, we have an equation that involves a derivative. Okay? That's all that is. And the goal here is to figure out what dy dx is. Right? What the slope of the tangent line is. So now we're going to solve for dy dx. And notice that this is 2 times y times dy dx. So don't let that throw you off. So now what we're going to do is subtract our 2x. So we have 2y times dy dx equals negative 2x. To get dy dx by itself, I'll divide both sides by 2y. Negative 2x divided by positive 2y is negative x over y. Okay? So this is the formula for the slope of the tangent line to this curve, to this circle, at any xy ordered pair. Now, what we need to do is find the slope of the tangent line at this particular point. So sometimes what we'll do is we're going to say that we'll evaluate this expression at that point. We might put just a right bracket on it, and in the bottom right corner, we could put the ordered pair 3, 4. And all that means is we're going to evaluate this expression at this x and y value. Okay? So let's resume up here. And now, since we're talking about a particular slope, let's call this m. M equals, I'm going to plug in 3 for x and 4 for y, and we can see the slope of this tangent line is negative 3/4. All right? So we were able to find the slope of the tangent line to this curve that's not a function through the use of implicit differentiation and solving for dy dx.